Another system where we have electric potential energy is the electric dipole placed in a uniform electric field. Now we will discuss this and see how energy is stored as the dipole is in this electric field. Now electric dipole, we have encountered this before. It's just a system consisting of two equal and oppositely charged point charges. So we have 2 point charges, equal and opposite, and they have this separation between them which is equal to 2a. Now we define a quantity which is called the electric dipole moment, and it's a vector. This is of course something of convenience for us. This is why we define it, because while the dipole is actually the end two charges is composed of 2 point charges, but we prefer to treat it as a single entity. Okay, and the reason for this is that dipoles appear naturally in molecules. Okay, so when you have a molecule, for example, the overall molecule is neutral, but some molecules, they are polarized in that the positive charge and the negative charge are split, and in this case this is a naturally occurring dipole, and therefore in treating these systems it is better to treat the dipole as a single entity, because its behavior actually is due to this nature. I mean, these two charges, equal and opposite and split together, this fact determines how it behaves in electric fields, and therefore we treat it as a system together rather than looking at it as just 2 point charges and treat it as each point charge independently. Okay, so this is why dipoles are important. So this dipole moment is something that we define about a dipole. It's a vector that goes from the negative to the positive charge, so, and it's directed in this way, and the magnitude of this vector is just the distance, the separation between them, multiplied by the one of these charges, which is the positive charge. Okay, so this is a positive quantity because it's a modulus of a vector, and its direction, it's important. It's a convention from the negative to the positive charge. This is how it goes. Now we assume that we have this dipole and it's placed in an external electric field, and it's placed somehow at some instance. It is such that placed such that the dipole moment vector makes an angle theta with the electric field, and it's aligned this way. Now evidently this is a uniform electric field, and so each of these charges will feel an equal and opposite force, and this force will be just equal EQ. Okay, the magnitude of this force is equal EQ. E, modulus of the electric field, Q, the magnitude, absolute value of the charge. The charge on the upper charge, which is the positive charge, will be to the right in this case, and here it will be to the left. Now these charges, these forces, are equal and opposite, and therefore they cancel each other. So the net force on a dipole is actually placed in a uniform electric field, because if the electric field were not uniform, these two forces would not be equal necessarily. Okay, is zero, but okay, the net force is zero, but the dipole in this case can rotate. The net torque is not zero. Okay, so it is very simple. If you have a rod, for example, centered and fixed at center, and you apply equal and opposite forces to the two sides of that rod, the net force on the rod is zero, so it will not have translational motion, but it will rotate. So because there is a net torque. And what is this net torque? Well, it is the torque due to this force plus the torque due to this force. Now what is the torque by a given force? It is F multiplied by this distance multiplied by sine the angle, which is theta in this case, because the angle between the direction of action of the force and the direction of the r vector in this case. So it will be sine equal to sine this angle at the same time. Okay, so because r goes from here to here, and this is F. This will be the angle, which is exactly the same angle. So it's F multiplied by this distance, which is A, multiplied by sine theta. And since the torque in this case, both torques are act in the same direction, okay? In other words, the rotational sense is clockwise in this case, so they add up together. And so we have twice Fa sine theta is the torque by this force, and it is the same by the second force. So you multiply it by 2, you get the total net torque acting on this dipole by these two forces. And you can express this torque in terms of the dipole moment, the magnitude of the dipole moment, where expressing F as QE, then in this case 2 AEQ will be P, so you express the torque in terms of the electric field and the dipole moment. This is why we introduce the electric dipole moment. Actually, it becomes an elegant expression, as you can see. So this is the net torque acting on this dipole. Okay. Now this net torque, it's modulus of P modulus of A multiplied by sine theta. This reminds us of what? Of the vector product, and the torque is already a vector, so we can actually express this torque as the cross product or the vector product of P, the dipole moment, and the E. The modulus of this will be modulus P modulus E sine theta, okay, where theta is the angle between P, the vectors P and E now. So this is the net torque that acts on an electric dipole in a uniform electric field. Now this system, if you think of a dipole, place the electric field, this whole field plus the dipole can be thought of as an isolated system. The electric field is a conservative field. So the forces that are acting are actually conservative forces. Okay, so when it is unisolated and there is no external force, and of course then the total energy of that system is constant. But what energy? Now we have seen that before, that when you have an electric field, you have charges, then you have an electric potential energy in this case. Okay, so here I expect this system to have a potential energy. Let's try to see what is type of potential energy is this. I mean, potential energy is associated with the charge and the electric field. So what type of potential energy? To understand it, let's assume that we have an external agent, an external force, or external torque is applied, and this torque is rotating the dipole in the electric field. In other words, this is your dipole. It will rotate in this direction, but if the external force acts and tries to rotate it clockwise, then that external torque will be doing work against the electric field. Okay, because this is going to rotate this way, you are forcing it to rotate the other way. Okay, so that's what you are doing. It's like, now what? If you have a rod attached to a spring, and this spring can be wound, and then you are trying to rotate that spring, and by doing this, you are winding you are trying to rotate the rod, and doing so, you are winding the spring. Okay, so you are doing external work, and this work is stored in the spring here. Here, because you are acting against the field, then you need external work to rotate this dipole. And this external work, therefore, means you are importing external energy to the system of field plus dipole, which is isolated. So you need to put extra energy. Okay, and this extra energy manifests as work. And when you do this external work on a conservative system, we know that this leads to what? Leads to a change in the potential energy of the system. Okay, so when an external torque is applied and tries to rotate the dipole, then that increases actually the potential energy of the system. So I write, okay, this external work should be equal to U final minus U, the change in the potential energy between the initial configuration and the final configuration. It's exactly like a rod attached to a spring, and when you are rotating, you are winding the spring, okay, and you are storing energy in the elastic potential energy in the spring. It's exactly the same. So this is the expression. So using this, by finding what is the expression for the external work, we will find what is we found an expression for the potential energy of a dipole in an electric field. Well, when a force rotates this by an angle theta, we know from mechanics that the infinitesimal work done as this is rotated by d theta is tau, the torque multiplied by d theta. We are assuming the torque is constant, and we are assuming that as this is happening, the kinetic energy is not changing. Okay, so the total work, this is the reason behind writing this. This is true only if that external force doesn't change the kinetic energy, because W external is actually delta U plus delta K. But if delta K is 0, then this is true. So this is the infinitesimal work when it is rotated by an angle theta. So what it is when it is rotated all the way, it is just the integral. This is your torque that's applied by external force, which is equal and opposite to the torque applied by the electric field. And to find the final work when this theta changes from theta initial to theta final, you just integrate. Okay? Now, although the force is constant, the torque is not constant. Why? Because the torque depends on theta, and as you rotate, theta changes. And therefore, you have to integrate. And this is what you do here. You just integrate this over theta. Theta is the only variable. And when you do this, you get this expression. And this is U final minus U initial. Here it is equal PE cosine theta initial minus PE cosine theta final due to this minus sign. But it should be final minus initial. So actually this is equal minus PE cosine theta final minus PE cosine theta initial. It's evident that you can write this. If you want it to be consistent with U final minus U initial, then you have to have the quantities referring to the final first minus the quantities referring to the initial. So you write this as minus PE cosine theta final minus PE cosine theta initial. Using this, the expression, this gives you an expression of what is the potential energy of a dipole that is in a given electric field. It is this expression. U when the dipole is aligned so that its dipole moment makes an angle theta with the electric field, then the potential energy of that dipole is equal minus PE cosine theta, which can be written as minus P vector dot E, which is the scalar product of the P and E. So this is our expression for the dipole in the potential energy of a dipole in an electric field. This is not a new form of energy or whatever, no. At the end, this is electric field, and we have a system of charges there, and this is for this particular system, this is the expression for the potential. It is the electric potential energy. It is not something new, okay? But this is its form in this case. And this energy is minimum. It becomes minus PE when the dipole and the electric field are aligned together, and it is maximum, it is plus PE when the electric field is aligned across the dipole, which makes sense actually, because when the electric field is aligned across the dipole, against the dipole is aligned against the electric field, any change in this case, if you just give it a push, it will rotate and try to align itself parallel to the electric field. It will rotate in that direction. And in this case, when it reaches that position with maximum minimum energy, it will have the highest kinetic energy in this case. Try to think of it, okay? And therefore, the fact that when it is aligned against the electric field, it is the place where it's storing the most of potential energy, so it makes sense. And the least storage of potential energy happens when it is aligned to the parallel to the electric field. The dipole moment is aligned parallel to the electric field, because in this case, any disturbance will come back to the same position. It is the equilibrium position. So this is the potential energy for the dipole. Before closing, I would like to tell you something about what happens to a dipole really when you put it in this electric field, even without having an external force or exerting a torque. think of a dipole. Assume that somehow you align this dipole here and you put it in this electric field. What will happen? The field itself now it has a potential energy here. Okay, it has a potential energy already. Why? Because the potential energy is P dot E minus P dot E. So minus PE cosine theta, it will be its potential energy. And this is above the minimum, because what is the minimum? The minimum is minus PE. So minus PE cosine theta in this case is greater than minus PE. Minus PE is the smallest, okay, in negative, because the most negative. Minus PE cosine theta, where cosine theta now is less than 1. So minus PE cosine theta is greater. It's still negative, but it's greater than minus PE. So this has potential energy. So any system which has potential energy, if it's allowed to, it will change in a conservative system. It will release this potential energy into kinetic energy. So if you release it, there, as you can see here, the field will exert a torque, and it will start rotating. As it rotates, it will speed up, and it will reach a point where it is aligned along the direction of the field. In this case, its potential energy is minimum, but it still has kinetic energy, so it will continue moving. And as it continue moving, it will move in this direction, in this case. And as it continue moving, in this case, it will slow down, okay, until it gets oriented. The dipole moment will be oriented in this direction. Slow down until it stops somewhere here, where its energy, in this case, kinetic energy will be 0, but it has potential energy. And it will rotate again in this direction, because the direction of the torque will be rotated as it crosses this line. And then it will come back and reach this point where it will stop again, because all the kinetic energy will be depleted, and so on and so forth. So this dipole in this case will be dancing in the electric field. It will start this way, go this way, come back this way. Okay? So if you put a dipole in an electric field, it will dance in the electric field. Okay? So that's what we can say about dipoles. Before you go ahead, you try to check this checkpoint.